So it's my pleasure to introduce Professor Jeff Vitter from University of Mississippi, where he's a distinguished professor of computer science. He's held various faculty and leadership roles at Duke University, Purdue, Kansas. He was most recently the 17th Chancellor of Ole Miss, University of Mississippi. I may have missed something.
Yeah,
sorry. He has 4 decades of research and academic kind of service career, and he's one of the founders of so-called big data and data processing algorithms before big data was a thing. Most recently, he's been looking at the link between prediction or learning and data compression, and he's going to tell us about some of that work.
Yeah, great. Thanks, Paul.
Get away.
Yeah, so I've been working on big data before big data was cool. And I'm going to really talk about prediction and learning today. And there are kind of 4 main areas of big data that I've been interested in during my career and have worked on. The first is external memory algorithms, how to design algorithms that are efficient in terms of using locality and parallelism of disk drive, for example, so that the communication bottleneck between the disk drives and the internal memory is minimized, because that's the bottleneck in many computations. The same thing happens in levels of hierarchy within the computer. So how to exploit locality to speed up algorithms by orders of magnitude. From there, I got interested in data compression, dealing with space issues. And then compressed data structures is a third area where the goal is to not only reduce the data structure size dramatically to be, say, more related to the compressed version of the input size, but be able to also act directly on the data structure in compressed format. So, for example, we worked on a compressed suffix array, and we developed the first provable structure whose size is more or less related to the entropy or the compressed size of the text that it's indexing, but the data structure itself is indexable. It can be indexed and can be searched. So it is an index, and you can throw away the original input and only deal with this compressed version, which not only can reconstruct the original string, but without reconstructing anything, you can probe it directly and search it. And that's led to a variety of approaches in this general area of succinct data structures or compressed data structures. But what I'm talking about today is an application of data compression into the learning domain. And we're working on some applications now in various domains, seismic, virtual reality. And I keep coming back to this main paradigm that I worked on before with joint work with P. Krishnan and Ken Kerwitz. So I'm going to go back to this basic relation that I think is so fundamental because it comes back and is the driving motivation and paradigm for a lot of interesting ideas that we're working on even today. So it's all about prediction learning as data compression. In particular, let me give you an example. You probably know the famous fable of the 6 blind men trying to describe what an elephant is or learn what an elephant is. The first blind man feels the side of the elephant and concludes an elephant must be like a wall. The second blind man happens to touch the elephant at its tusk, and feeling the tusk concludes that an elephant is like a spear, and then so forth for the other 4 blind men. Well, they only saw one aspect each of the elephant, and they didn't collaborate, so they didn't have really a good idea of what an elephant was. So let's talk about what it means to learn. And for the talk, I'm going to illustrate everything in terms of prediction. Prediction and learning are really the same thing. Prediction is merely learning a sequence. Given a sequence of items that you've seen today, what is the next item in the sequence? So prediction and learning are really synonymous. And to start off and give you an intuition, let's consider a simple case of concept learning. So I'll be the teacher, and I'm going to present you, the students, with a bunch of examples of a concept and non-examples of a concept. So I'll tell you in each case, is this picture a positive or a negative instance of the concept we're learning? And we'll use the elephant example. We're going to try to learn what is an elephant. So I'm going to show you some examples. Here's the first one, and I'm going to label it positive. Yes, it is an example of an elephant. Here's the next example. No, this is not an elephant. The third example, yes, it is an elephant. And, you know, this example is actually very timely given that the big elections are coming up next year. A lot of people are spending a lot of time now trying to determine what an elephant really looks like. So that's what we're doing here. Here's another example. Definitely not an elephant. Okay, one more. Yep, that's an elephant. And then let's conclude with the sixth example. No, that's a negative example, not an elephant. Now, you can go through a number of these things, but mathematically and concept learning, you can prove that for a given concept in a certain class, if you use so many random examples from whatever distribution the teacher chooses, then the learner, after a reasonable number of examples, will have a very high probability of being able to correctly classify a picture never before seen. And essentially, this intuition is showing you that learning, this concept, and data compression are the same thing, because if you as a learner are now given a picture and not told whether it's an elephant or not, you're going to have a good chance of determining or answering what it is, because what you have done is essentially compressed what you've seen into a few basic rules, like an elephant is very big. An elephant is usually gray. You know, most of the pictures of an elephant were gray, not that one. An elephant does not have feathers. And just with a few rules, now if I'm giving you a new picture, you're going to be pretty accurate in determining whether or not it's an elephant. Moreover, if you did not compress, if all you did was memorize the pictures you've seen, you'd have zero chance of classifying a new picture that you never saw before. I mean, unless it's exactly one of these, you're not going to be able to learn. So learning and data compression are synonymous. You can actually prove that in the field of probably approximate learning in a fairly general setting. If you're able to learn a number or observe a number of concepts, examples, and then form a hypothesis that is strictly smaller, like related to the root, like square root in size compared to the full number of concepts, then if your rules are consistent with everything you've seen, then with high probability, it will give you the right answer on new queries. So we're going to look at prediction now as an example of learning and using our data compression motivation. You can liken this to a 900 number, which became popular over the last couple decades. So 900 number, you pay money, so it costs something to be able to predict. But what you get is some useful information, like you might get information about what? In particular, we're going to look at prefetching, which is paging, figuring out what page do I want to put in cache. You might get a hint when you're shopping online. You might, perhaps in virtual reality, learn what is the user interested in so you can zero in and grab more detail around that area so that when the user turns his or her head, that detail will be there. you might predict when something happens, which is useful for determining when to spin down a disk, when it may not be needed, or when to power down components on a mobile device in order to save power, or when to invoke a security alarm because something has come into a screen that warrants a security alarm. Or you might predict how much selectivity estimation, for example, in a relational database, or how much gas or minerals are there in a certain region using seismic data. So we're going to look at the prediction problem, and in particular, here's the domain that we're looking at. This is just a simplified version of the problem for exposition purposes. I'm assuming there's a cache of memory. It could be internal memory, this could be disk, or this could be an L1 cache and higher levels of memory. Let's say it has size K, and the slow memory, the larger memory, has size alpha, much bigger than K. And let's just suppose we have the time to bring into the cache any items that we might want to bring. And the reason we want to do that is the access time in the fast memory is orders of magnitude faster than in the slow memory. And if we're able to get an item here that the user wants, then instead of having a fault and having to spend orders of magnitude more time to get it from here, it's already in memory. So we want to maximize the number of hits where we have the item in memory, and similarly minimize the number of faults. So we're going to measure the effectiveness by the fault rate, which is the percentage of time that we have a miss. Fault rate is number of misses divided by the total number of accesses. So there's a lot of work on prefetching. Generally, they've been empirical. They're not backed by any theoretical analysis or guarantees. Similarly, in learning theory, there's this concept learning domain where a lot of interesting work has happened, but not looking at this prediction problem. So this is the first work that really equated prefetching with data compression to develop a universal method. So let me just explain by what universal means. This prefetching method will know nothing about the source. It will do as well as if you knew total information about the source. So it's a very powerful approach, and we're going to show that it's optimal in the limit. So here's another intuition of data compression and learning, or prediction, that I think will be very immediate. Now, in data compression, let's think of text compression. We're compressing, and typically a lot of compressors work this way. They see a sequence of text, they've compressed everything up to a point, and then they're going to compress the next character or the next set of characters based on what they've seen. Okay? We're going to equate that to prefetching, where imagine instead of a sequence of characters in text, imagine your characters are just page numbers from the universe of pages. And what we're going to do, given the sequence of page numbers requested by the user today, we're going to predict what the next page number is that the user wants. And if we're successful, if we bring that into cache, we'll have a hit rather than a miss. So how does a data compressor work? Well, suppose these 12 characters in green are the characters already seen, and now the next character has to be compressed. Well, how some data compressors work is that suppose A is expected with high probability by the compressor. Well, the compressor is going to allocate a very small code word, very few bits, if A actually is the next character. And it's going to reserve larger code words for those characters that it expects with small probability. And when it's all said and done at the very end, if the compressor is good, if it has compressed well, that means its predictions are probably pretty good, have been good all along. So that's the idea behind it. And ziv-lempel in particular is a method that is theoretically optimal in the limit and performs well in practice. And we're going to use that as a basis for our prediction. So here's how the ziv-lempel method works. If you're familiar with the Lempel-Ziv, this is a review. If not, it's really a beautiful approach and method that I wish was taught more in elementary courses. A fundamental notion that's an incredibly powerful notion is around arithmetic coding and coding in general. I'm not going to go into arithmetic coding, another beautiful idea, but think of it as a black box, sort of a continuous version of Huffman coding that allows you to encode an event or a character that you expect with probability p using log of 1 over p bits. So think of it as a black box that can do that. This may be a fractional number of bits, but arithmetic coding is actually capable of encoding things with a fractional number of bits. So as an example, ASCII coding codes characters from an alphabet of size 256. It implicitly assumes every character is equally likely, so it assigns log of 256, log base 2, of 256, which is 8 bits, to each character. So ASCII is an encoding where every character is implicitly equally likely. If some characters are more likely, like suppose the letter E occurred half the time, then we would want to encode E with log of 1 divided by 1/2, or log of 2, which is 1 bit. And we would code the other characters with many more bits. So we might encode E with the character 1, and every other code would start with a 0, for example. So here's how Lempel-Ziv works. Suppose we've seen the 12 characters to date, and we've actually parsed them along the way into substrings. Now, Lempel-Ziv operates by compressing the next set of characters, and that set is determined by marching forward as long as what it has seen is already one of the previous substrings. So when I look at A, I notice that A is a substring already. When I look at AB, AB is already a substring. ABA is already a substring. And the first time we have a new substring is with that fourth new character. That becomes the seventh substring in our parse. And we encode that substring by a pointer back to the longest matching substring, which was this ABA. And since there are 6 substrings, that pointer takes a logarithmic number of bits. Even though this is a fractional amount, just think of this as log of 6 bits. And we're going to encode that last character just in ASCII using log of alpha bits, where alpha is the alphabet size. You can think of that in the arithmetic coding world by, here's a data structure that Lempel-Ziv actually uses. This represents the data structure at this point, before we've seen this string. There are 6 leaves corresponding to the 6 substrings. It's just a trie data structure where every transition is labeled by a character and a probability. So when I follow this string, I simply march down the tree until I get to a leaf. So I follow A, then I follow B, then I follow A. I hit a leaf. I know that this is the longest match. And notice that every leaf here has probability 1/6, because the path here, if you multiply these probabilities, they telescope, and 5/6 times 3/5 times 1/3 gives you 1/6. All of these leaves have probability 1/6. And implicitly, I can encode this path to the leaf with log of 1 over 1/6 bits, or log of 6 bits. And here's how we update the tree. As we march along, we just merely update the count. So now notice that before, 5 out of 6 of the clauses started with A. If you notice, the first 5 clauses started with A. 1 out of 6 started with B. This new clause also starts with A, so now it's 6 out of 7, and B is demoted to 1 out of 7. And here we've added the new internal node, and this leaf represents a string that actually ends there. Now we have 7 leaves. So that's how the simple Ziv data compressor works. Any questions on that? So let's use it to prefetch. We're going to simulate exactly what the compressor is doing. Imagine that we're at this point, these now represent page numbers. I want to figure out what is the next page number that's going to be there because I want to bring it into cache. This is an example there where there are only 2 pages and the cache is of size 1, just for simplicity. Well, at this point, I'm at the root and I'm looking at the 2 transitions, and I'm simply going to take the one that has a higher probability because A is 5/6 likely to be that next character, whereas B is only 1/6. So notice that the tree version converts the Ziv method, which is Ziv encodes an entire string at a time. This converts it to encoding a character at a time. So I'm going to put A in the cache because it's more likely. Lo and behold, the next character is an A, so I'm correct. There's no fault. I move down here, and now I'm ready to predict the next character. I think it's B with probability 3/5. It turns out to be B, so that's good. Another hit. I move down here. Now A and B are equally likely. This is kind of an anomaly, just representing that there is a clause, a string that ended there. A and B have the same probability, so I flip a coin. It happens to be A, so I move down here, update the tree like I did in the last slide. For this character, I just flip a coin. Once I reach a leaf, anything's equally likely, flip a coin, and then I position myself back at the root for what comes to follow. So that's the method for prefetching. Depending on how much time you have, you might prefetch as many things in the cache as the cache can hold, or you might just prefetch what you have time to do. And for various reasons, after a number of accesses, you actually throw away everything and start the data structure over. So we're going to examine why this actually gives you optimal performance for prefetching, knowing nothing about the source. So let's talk about what the source looks like. And actually, we've done work where we've looked at worst case situations. But here, we're assuming that the source is a Markov source. That's a little more general than a Markov chain. A Markov source is nothing more than a finite state automaton. So you can imagine an arbitrarily complex finite state automaton. Here we just have a trivial example of two states. Each state has transitions coming out of it labeled by a character and a probability. And this generates a string by simply, for example, here, with probability 1/2, I follow this arc and emit an A, or with probability 1/2, I follow this arc and emit a B. Well, suppose I emit the A, then I've moved over here, and then I continue the process. With probability 0.2, I emit a B and stay here. With probability 0.8, I emit an A and move over back to that state. That's how the sequence is generated. So the sequence is a probabilistic sequence. And every state kind of looks like this. For every character in the alphabet, there's a transition out of it, and there's a certain probability on that arc. That's how the source looks. Yeah.
Does it ever make sense to sort of stop building your tree and just use what you have so far, rather than adding new states?
Yeah, you can do that. You lose a potential change in behavior of the state. And I mean, in practice, that can happen. If you know that the source is fixed and is probabilistic like this, then you might want to do what you described. Yep, good question. Okay, so suppose now you know what the state is. The prefetcher knows nothing about the state, doesn't know how many states there are, doesn't know the transitions, probabilities, or anything. Suppose that you actually knew the state diagram and the transitions, the probabilities on the arcs and everything. This is the best you could do a priori to compress. Basically, you could just follow through the state. You knew what state you were in. If A was the next character, then you just follow that arc to the next state. At any given point, you're on the same state as the source, and you know the probabilities coming out of it. So you can allocate log of 1 over p bits, which is the same as negative log of p, to every arc that has probability p. So for character C, you would allocate log of p sub c bits to encode the C with the negative sign out here. Now, the probability that you actually see character C is this probability. So the sum of these terms is nothing more than the best possible encoding for the next character if you're at state C. That's using that notion that to encode an event with probability p, best thing to do is use log of 1 over p bits. This is merely normalizing by which state you're in. So this term is the well-known entropy of the source. It's the best you can do a priori. Our the Ziv-Lempel compressor in the limit achieves this kind of compression. Now, in the fault domain world, in prefetching world, we are interested in the fault rate, and the analogous best possible compression ratio is the best possible fault rate. And you get the best possible fault rate is similarly computed. If you're in a given state Z, if I knew what the source was, then what would you prefetch into memory if you knew where you were in the state diagram? You would just look at the arcs, and let's say you could prefetch k items, fill the entire cache. You would take the k transitions that had the highest probability associated with them, right? So if these are ordered by probability, you would take the first k of these arcs, and those characters that label those transitions are the ones you would move into cache. And this is merely saying that you have a fault if these are the ones you put in cache. If the page that occurs is not one of the k most probable, you have a fault. And you're normalizing or you're multiplying by the probability that C is the actual character. So this is analogous to this expression, except instead of measuring number of bits per encoding, you're measuring either I have a fault, which is a 1, or I have a hit, which is a 0. Okay. So we want to show that our predictor, our prefetcher, in the limit achieves this fault rate, even though this fault rate is kind of cheating because it uses knowledge of the model, uses complete knowledge, and we know nothing about the source. So we're going to show that our prefetcher converges to that optimal fault rate, and moreover, if our source is ergodic, it's the case that for almost all sequences, namely for the fraction of sequences that do not come close to this optimal amount is negligible and goes to 0. And moreover, we can show an even more nuanced result, and that is, if for some reason the model I showed, the one that uses knowledge of the source, is not the best for a particular string because maybe the string is pathological for that model, and there's some other prefetcher that does better, then our fault rate on our prefetcher still converges to the very best prefetcher, even if that prefetcher is kind of tuned for each individual string. Okay, so we're going to do this by first proving that we're going to kind of look at the basic ideas of what's behind the Ziv-Lempel proof of optimality in terms of compression. Ziv-Lempel is a good compressor because the Ziv-Lempel compression is no more than the optimal compressor that you would get if you had knowledge of the source, which is cheating, but if you had knowledge, this would be the optimal. It's no more by an amount that goes to 0 as a fraction of n as n is large. Similarly, we're going to show the same result in terms of fault rate. Our prefetcher is going to be basically in the limit the same as the optimal. So let's see how that is done in the case of ziv-lumpel. Well, given a sequence, sigma, you know that ziv-lumpel parses that sequence into substrings. Let's say there are C substrings. The alphabet size is alpha, and B is the best compressor, namely the one that knows the source. Well, we just went through how ziv-lumpel works, and every time you encode a new substring, you do that with a pointer back to one of the C previous substrings using log of C bits. There are C substrings, so per character divided by n, this is basically the compression. You can ignore the little ASCII encodings of those new characters at n, because that's...
Wait, sorry, what is n?
N is the number of characters in the sequence sigma.
Okay.
Yeah, sorry, I forgot to say that. And we're gonna show the idea of why that is actually optimal, because we're gonna show a lower bound that the best compressor that knows the source has to use this many bits also. Therefore, ziv-lumpel is basically optimal. So why is that the case? Well, let's go back to our example where we've seen the 12 characters. They were parsed into these 6 substrings. And depending on the probabilities we associate with each substring, we're going to encode any one with log of 1 over the size of that interval. Now, ziv-lumpel gives the same weight, 1/6, to each of those substrings. So we're going to use log of 6 bits to encode a pointer to one of those substrings. Now, it turns out that the best possible compressor has to use at least this many bits, which is essentially C log of C, all divided by n. And the reason for that is, here's how the proof goes. There are C substrings. Let's look at all pairs of states in the finite state diagram. Let's say there are S states, so there are S squared pairs of states. Let's take an arbitrary pair, Si, Sj. There are S squared possible choices. So for that given pair of states, consider out of the C substrings, consider the X substrings that actually start at that state and end at that state. Let's call that number of substrings X. Then we know that the best you can possibly do from that arithmetic coding lemma is to encode each of those. The minimum coding is when basically all the intervals have the same size. You can play around with that. But the total encoding, if I have to encode all 6 of those things, the encoding is actually minimized if they're all the same size and are given equal weight. So therefore, to encode these 6 or these X substrings takes X log of X bits. And by convexity, you can show that if you're trying to minimize the complete encoding is minimized when X is the same for every pair of states. So in other words, X is C divided by the total number of states, pairs of states, S squared. And if you multiply this times this, you end up with, this is a total output size as a lower bound. Dividing by n gives you the compression per character. And therefore, the optimal compression has to be at least that amount, which is essentially what ziv-lumpel achieves. Okay? So analyzing the fault rate is actually somewhat complicated because, imagine the source. You're going from state to state, emitting characters, following arcs. the ziv-lempel prefetcher doesn't actually have the same states. It's got this tree. So when you're in a given state, and you may come back to that state many times, in the tree, you may be at different nodes in the tree every time you're at this same state. So you're comparing the probabilities on the arcs at a given state with probability estimates that are at different nodes in the tree. So it's a little more complicated, but without going through the mathematical details, the intuition is that you can actually upper bound the difference in fault rates between our prefetcher and the optimal one that knows the source, the one that cheats. That's bounded by the sum of the differences of the probability estimates. So ignore the fact that the probability estimates for our prefetcher are coming from different nodes each time we're at a given state. So let's just say we're at state Z, and think of these estimates as being more or less not changing every time you're at the state for simplicity. The difference in fault rate is related to the difference in absolute values of those probability estimates. These are the estimates, these are the source probabilities that generate the next character. This is our estimate for them, that the next character is I. Now, in the compression world, we have a similar thing that a source generates the next character with probability, if it's character I, with probability log of pi, negative log of pi bits, and that character occurs with this probability piece of I. The ziv-lempel prefetcher, though, doesn't know the exact probability that I occurs. It has an estimate Ri. So we're subtracting the ziv-lempel compression length from the optimal compression length. And the difference of two logs is the log of the quotient. So that's exactly this expression here. That's the difference between the encoding of the next character I of optimal versus the ziv-lempel. And multiplying by the probability that the character is I over all possible characters gives you the compression. This is the actual difference in compression for the next character from state Z. If you call that delta H, and generally this is going to be a small number because ziv-lempel works well and the difference goes to 0 relatively, then we can bound this prefetching difference by square root roughly of that number. So delta H is a small number, square root is a bigger number, but if this is going to 0 as a function of n, then this is also going to be going to 0 as a function of n, just not as fast. So because this is small, and that's because we've shown ziv-lempel is a good compressor and that goes to 0, we get similarly a bound for the prefetcher. This is just kind of a high-level intuition, but the basic idea is there. So our prefetcher is optimal in the average. Now we can actually show almost everywhere convergence by, after n accesses, throw away the data structure and start over. If you do that b times, then by using the ergodic theorem, if we have such a source, then we know that the average of the fault rates over the entire sequence, over all the blocks, that average is the fault rate of the entire sequence. But by the ergodic theorem, that fault rate is also the expected fault rate for any given block. And that expected fault rate we just showed goes to this amount in general. Therefore, for almost every sequence, the actual fault rate is converging to this amount, not just the expected value.
But don't you need to have your n going to infinity? I mean, it seems like if you're just resetting, if you're resetting after the same n every time, you're not going to converge, right?
You do, yeah. N is going to infinity as well.
So if you're actually doing this in practice, you reset after n, and then after some larger number, and after some larger number, and after some larger.
Yeah, you could, theoretically, you would do that in practice. You would reset based on memory constraints or something like that.
Another question,
Mm-hmm.
What if the sequence you're observing is actually a combination of multiple independent interleaved sequences? So it's not, you chop it up into sequential buckets, but suppose that it's generated from n different users and each one has one.
Right.
Would it apply or?
In that case, if you knew nothing about the interleaving, or you didn't know that there was an interleaving, the best you could do was achieve the entropy of that combined source. So the entropy would be a higher number than if you knew that they were actually interleaved. Well, now let me think. If you have a finite number of interleaved sources,
You can still define
Yeah.
it. You can still describe it with a finite state system.
That's
the same
right.
way.
That's
you just
true.
have a
But-
product. You take the products of the states for each.
But
That's
finite
true.
state assumes that transition probabilities are just fixed given the state and not additional variables. Like, I mean, a use case, for example, is suppose you're predicting what videos users will watch next. And there's
Yeah,
multiple
I mean, if you-
various different interests, right?
It depends. It depends if you interleave in a worst case way or if there's a probability distribution on what
Stream.
source you're choosing from next. If there's a probability distribution, then like you said, you could kind of join them all together in this giant finite state atomic, which is still finite size, and it would have a certain entropy. So, and yet one more nuanced idea is that even if you take a given string produced by this Markov source, it may be because the string is an unusual string for the source, like you're getting low probability characters emitted, that there's some other prefetcher that does better than what would be normally the optimum one. Well, it turns out that really happens with exponentially small probabilities. So our prefetcher is still going to converge to that very best prefetcher, even when you can tune the prefetcher for the individual sequence that occurs. Now, if the source structure is known, then you can follow the paths. And if you don't know the probability transitions, you can quickly estimate them by simply keeping statistics at every node of what the next character is. You converge much more quickly to the optimum that way. And in practice, methods based on PPM, which keep track of statistics like n-grams and so forth, converge faster for prediction purposes. Here are just some experiments on different traces. A typical one is, here's a CAD trace where using LRU only as a cache replacement strategy with no prefetching, the fault rate was about 85%. Using just one prefetch per access, the fault rate drops to under 40%. It actually doesn't decrease much if you prefetch more than once per access in this example. And similar results for the other traces. This trace had not as much of an improvement. It really varies by the kind of entropy that's sort of exhibited by the individual traces. But the performance was very good in practice. In each situation, we're using LRU as our cache replacement strategy. And that's an interesting open question, is the interaction between prefetching and cache replacement. Because if you prefetch something, you have to determine what you're kicking out. And if you have a choice of what you're kicking out, then there are different approaches you could take. So let me conclude by basically saying this is what we talked about today, using this intuition that data compression and prediction are really the same thing. We took the innards of a data compression method, zip-lemple, and we used that to predict and got an optimal predictor, assuming the source was Markov, which seems to actually work in practice. Interestingly, we can now prove that a similar result even when the source is not generated by something like a Markov source. If the source can be worst case, no structure to the source whatsoever. So if I can take an arbitrary string of length n and I'll come up with a prefetcher that's going to be optimum. Now, what is it optimum against? Well, to be fair, you can only compare against prefetchers that have kind of a finite size, because if the prefetcher had as much state information as the length of the string, it could memorize the string and always be right. So if you have a finite state prefetcher, which sort of looks like the source diagram in the previous part of the talk, then our prefetcher will be optimum against any prefetcher from that category, even though the source is an arbitrary string. And it's interesting that the method is actually different. It doesn't just put into cache the characters that have the highest probability. It actually has to boost, it takes the probabilities predicted for the characters, it boosts them to a very high power, and then it picks randomly using those weights. And the reason it does that is because the worst case nature, you could trick it otherwise to be kind of always bad.
Right, like you could sort of compute up front, what are the 3 highest probabilities, and then take the fourth.
Yeah.
Choose the fourth.
And if they're kind of really close to one another, if one is near the borderline but it just doesn't make it, you're often making a bad choice. So I mentioned the interesting interplay with cache replacement, and I started the talk by mentioning that there are applications of prediction that fundamentally come down to wanting to represent things with a small representation that gives you a good basis for predicting what is to come. So I appreciate the opportunity to visit, and then I'd be happy to answer any questions.
Maybe we can start with remote questions, if there is any. Or questions.
If nobody minds, I just wanted to ask, so could you use this, in fact, to replace the cache replacement algorithm by, say, rather than flushing least recently used, flush the one predicted as lowest probability?
Yeah, there are some folks, I think they were at Santa Cruz, I don't remember, that develop cache replacement algorithms based on these kinds of prediction methods. So some people have looked at that.
Although I guess, yeah, I mean, this tends to work best when you have a relatively small number of pages. If you have some huge number of things and they're not getting read very many times, then this is less useful. But then the entropy is really high, so.
Right. Mm-hmm. And then this is not exploiting things that you would want to do, such as algorithm designers who want to have efficient algorithms when dealing with external memory know that accessing items with locality helps. So you might want to access consecutive items. You don't want to have total random access all over the place. When you access one item, it helps to access other items nearby in blocks, because blocks are how items arrive into memory. So if you're accessing a sequence of items consecutively, it would help to build in kind of a prediction that the next item in sequence is likely to be that next access, even though you may never have yet accessed it. So you would want to, in practice, kind of build in other hints like that as well. Yeah.
So I'm still going back to the question about multiple users. Suppose YouTube wants to predict what people will watch so they can prefetch it, cache it. and let's say you have 1 billion videos and 1 billion users,
Yeah.
and you're trying to predict the traces of whatever, those 1 billion people. I'm still finding it hard to believe without knowing anything about the users, you would do optimal prefetching, given that their decisions are most likely highly personalized, context dependent, and will vary from any given point of time, devices and all of that.
Right. Well, if the sequences interleave in some random way, then was said, you could construct a larger finite state diagram that would be kind of a product of all the finite state diagrams, so it would be very big. And if you have a lot of users, that might be too big a structure. So in practice, you probably wouldn't want to do that. So in this example, do you know which user, does the system know where the requests are coming from? Like the user that the requests are coming from?
I guess depends on when you're doing it. If you're trying to prefetch tomorrow's watch time, probably not, right? But if you're trying to do something in real time, you might.
Yeah.
I mean, also for recommendations, I guess you're trying to figure out what users.
But when there's a
see.
request, the system knows which user the request came
Right.
from. So the system could keep a good estimate for each individual user. Now the question is, you know, with fairly good chance what for every given user, what that user will want next. The question is, how do you interleave those? So the interleaving, if you had a way of determining how things interleave or who's likely to make the next request, then you could do pretty well because you'd have a good idea for that user what that user wants next.
I think in this case, like what we have is like each user has got their own sequence, which is
Yeah.
really small.
Yeah.
And you want to kind of combine the learning from the other users and apply it to this user.
Yeah,
Right. And we don't have this really long sequence that you're trying to predict.
yeah, it seems like if you have many users, then really all you're kind of, and you don't really know who's coming up next, then all you have is just a probability distribution on what gets watched overall, and you just cache with the most probable things. And that's probably what this would converge to.
Yeah, but I find it hard to think that will be near optimal if you did the global priors.
It depends on what information you have that way.
Learning, like you have a limited amount of space, and so your optimality is with respect to what's there. So if you give me something totally random or hard to predict,
Yeah.
then the optimal is itself bad, right?
Yeah.
So it's only to within, I mean, the compression is saying there's some representation here that we could learn. It's only with respect to that best representation. So in your example, that representation itself could be near random, in which case you're only doing as good as near random.
Yeah.
I don't know if that makes sense. I think that's what's going on.
Right. It's essentially finding out the entropy or the compressibility of the source or the inherent predictability of the source. If the source is not predictable, then it can't do any better than if you had perfect knowledge of the source. Well, perfect knowledge of the structure, but not the probabilities of the source. The worst case situation is a different model. There is no source. It's just the worst case, an arbitrary sequence. You have to do special things to prove optimality with respect to a class of finite state predictors.
Earlier you mentioned the link between prediction and learning or compression and learning. So in many learning scenarios, you have additional, so compression minimizes the data compression loss. So it tries to encode the data. In learning scenarios, you might have auxiliary utility functions, things like not just minimizing the prediction error rate, but also ensuring that the model is fair, there's no biases, which the data might have. How would you go about incorporating such auxiliary criteria?
Yeah, that would depend on the particular instance. If you could build it into an optimization function, then you could compute some notion of optimal performance and hopefully get something that converges to that amount. But it would depend on exactly what you're trying to achieve. So in this particular example, we were looking at really two measures. One is the compression length, which is this is a difference in compression. This is the Kullback-Leibler divergence, also known as that. And we're looking at difference in fault rate, which is something that looks like that. And but if you had some other measures, you'd have to incorporate that somehow into the optimization function.
So suppose, for example, you don't want the compression algorithm or the prediction algorithm to favor just the frequent things because that might bias against some aspects. So you might want to have a guarantee that the compression is going to be within some margin for anybody, regardless of.
Well, if you want to speed up accesses, you do want the most probable event. Now, if there's some notion of fairness, then yeah, that you have to build that in some other way.
On top of it.
Yeah, you could change things around the build-in a notion of fairness. It would just change the analysis. You wouldn't do as well in terms of fault rate, but you would be instead optimizing some other measure.
Any other questions?
Great.
Okay, let's thank the speaker
Thanks.
again.